Cool. So we have a new lab today. We're starting the last lab of the semester. What is this lab about? Or what are we trying to study?
The equilibrium.
Yep. We're looking at an equilibrium, and what are we trying to determine with that equilibrium?
Like the what it was. Effect on entropy.
Yeah, we're looking at entropy, enthalpy, Gibbs free energy, and we're looking at thermodynamic values. So this is a bit different from kinetics. How do kinetics and thermodynamics differ? Does anybody have an idea? Or what are things you're keeping track of in kinetics? What's a big one?
Delta H.
Delta H does impact kinetics. That's also it's mainly considered a thermodynamic parameter. But in kinetics, what are you keeping track of? Like when we did that experiment with the dyes, I think it was experiment 6. What were you keeping track of? Or what things?
Absorbance.
We were keeping track of absorbance. What was the other parameter we were keeping track of?
Concentration.
Temperature.
Concentrate. Well, we were using absorbance and concentration synonymously. There was
The
one
wavelength?
other part, not wavelength. We needed a wavelength. So what else do you keep track of for kinetics? Concentrations and
Temperature.
nope. Well, temperature matters too. Temperature always matters. Okay. Concentration, temperature. Last really big thing.
Rate.
Rate. Yep. So rate. What does rate mean?
How
Like
quick
what?
the
What are
reaction, how quickly the reaction goes towards completion.
Right. So we're keeping track of time. Like how quickly is this reaction proceeding? In all the equations you've seen for thermodynamics, have you considered time at all? Like in class, do you see time pop up anywhere? Most likely, no, you don't see it. So thermodynamics is looking at changes in energy, essentially, where kinetics is looking at changes with respect to time. With thermodynamics, you actually want to conduct a thermodynamic experiment over a long course of time. We don't have a ton, so we're just going to look at it within a time frame of a lab. So these thermodynamic values, we've talked about some of them already. Talked about delta H. Give me another one. That someone mentioned. Delta G, yeah. Give me another one.
Delta S.
Yes, yeah.
And then we got, okay, our equilibrium constant. Let's talk about what each of these thermodynamic properties are. Okay. Delta S is probably the one that's the most easily described. What does delta S stand for? Or what does that delta stand for?
Change.
Yep, change in what?
Entropy.
Okay, and what's entropy? Does anybody have a good explanation for it?
Disorder.
Yeah, people equate it to disorder. What it is related to is actually the number of microstates or the possible configurations a system can be in. So a way to think about what a microstate is, you'd have a box, you throw a marble in it, you shake that box, and you open the top and you look at the marble. Each spot that marble could be in is an example of a microstate. So we'll use the term increase in disorder or randomness. Okay, what are these other things? Tell me one of the other parameters. What's delta H?
Enthalpy.
Change in enthalpy. Why is enthalpy important? Like, what is enthalpy?
tells you if it's exothermic or endothermic.
Yep.
Oh.
If delta H is less than 0, what does that tell us? Is it endo or exo?
Exothermic.
Yep. And what if it's greater than 0?
Endothermic.
Okay. What does exothermic mean? Like if I conduct an exothermic reaction, is the reaction vessel going to feel hot or cold?
Hot.
50-50 shot here, people. Good gambling odds. So hot or cold?
The vessel's gonna be hot, but like whatever's inside is gonna be cold.
Yep, well, the vessel is going to be hot. The system is giving off energy, right? That's what we're keeping track of. Is the system acquiring or losing energy? What about an endothermic vessel? Is it going to feel hot or cold?
Cold.
Yep, cold. It's drawing in energy from the surroundings. Now, inherently, have you guys ever talked about internal energy or no? Like, does delta U ring come to mind? Okay. So H plus D delta. I think that's right. So let's see. And enthalpy. So enthalpy is really related to something called internal energy. And people said that they haven't discussed what internal energy is, right? So this, by the way, this is for a constant pressure system, which we see in a lot of experiments. Internal energy can be thought of as like the total energy of the system. However, we can't measure this because we have influences from pressure and changes in volume. So in order to actually get something quantifiable that we measure in an experiment, we look at enthalpies. Okay. Delta G, what's delta G?
Free energy.
Yep, change and gives free energy. Okay, my purple's dying, so I'm going to switch to another color. Okay, so it's changes in Gibbs free energy. What does the Gibbs free energy tell us?
The reaction's spontaneous or non-spontaneous.
Spontaneous.
Yep. If the reaction's spontaneous or non-spontaneous, basically, will this reaction happen on its own without any energy input from us? If delta G is less than 0, is the process spontaneous or non-spontaneous?
Spontaneous.
Yep. And then this guy is non-spontaneous. Okay. So, is there an equation that relates these to one another that you guys know or should know?
Delta G, sorry,
Yep.
equals delta H
Mhm.
minus T delta S.
Yep. So you guys have talked about the system and the surroundings, right? So the system is the part of the universe that we care a lot about. What are the surroundings? So like, for example, I have a little bit of I got glue here. I'm not sniffing glue. I'm not promoting sniffing glue, but I have some glue. if this is my system that I'm exploring, what are the surroundings?
The container and like the outside air.
Yeah, everything else in the universe outside of it, everything else. But this little part of the universe that I care about, that's our system. Okay, so let's dive into what this equation actually means. So this is the entropy of our system, right? If we divide this equation through by T, get that. And entropy is related to a heat divided by a temperature. So this is entropy of system. This is also an entropy. What is this the entropy of?
Surrounding.
Yep, it's the entropy of the surroundings. And what about this guy? So this is the part of the universe we care about. This is the rest. If we add all that stuff together, what do we get? Which seems very grandiose and crazy.
Like the universe.
Yeah, it's the entropy of the universe. So what we're really looking at is a way to measure the entropy of the universe. We're seeing if the entropy is increasing or decreasing, which is pretty cool to check out. Okay, so we're applying this information to try and understand a chemical system, right? What chemical system are we looking at today? So what are we looking at? We're looking at an equilibrium reaction. What are we looking at the equilibrium reaction of?
Equation 1,
Yep.
the reaction of the cobalt chloride.
Mm-hmm. So has anybody ever seen cobalt in solution? Does anybody know what color it is?
Isn't it blue normally? In
Cobalt
solution or
Yep, cobalt chloride, like when it's paired up on, which side is it on? This side is kind of like a blue. On this side, it's a pinkish color. So to show you what it looks like, can everybody see my screen right now?
Yes.
This one where it's got the pink solution and the blue solution?
Yep.
Yeah. So this is what the two look like. So it's pretty cool to see. You can actually cause the transition to happen by adding more chlorine or taking chlorine away. So that's what we're going to be looking at today, is that system, that complex equilibrium. Okay. But we have to get some thermodynamic information from this. So what we're going to do is we're going to start looking at an equation. We're going to calculate delta G, and we're going to show how do we derive this Eyring equation where we can look at the equilibrium constant, delta G, and get other thermodynamic properties from it. So delta G can be calculated in a handful of different ways. The one that we're going to consider is looking at really fuzzy delta G. Come on, focus. Is starting with this expression. So this is delta G. What is that delta G naught? Like, what does this term mean? What does that little that thing up there mean?
At 270 degrees.
Yep, it's
Standard
standard
condition.
conditions. So change in gives at standard conditions. So this delta G is at some other point, so change in G. Other temp. And what is this? What's R again? So what's R?
Ideal gas constant.
Yep, ideal gas constant. T,
Temperature.
temperature. And this Q, what's that thing?
The reaction quotient.
Okay, yep, this thing's the reaction quotient. So it's a little bit different than the equilibrium constant. It is the concentration, it's like an equilibrium constant with before equilibrium is achieved. Now, this equation changes if we're at equilibrium. How does this equation change if we're at equilibrium?
Q is replaced
Delta
with
G
K.
0.
Okay, first one I heard was, what happens to Q?
It's K now.
Yep, it's K now. And then Phil, what'd you say?
But delta G is 0.
Okay, so this delta G is 0?
The other one.
Yeah, it's the other one. It's this guy that's 0. Okay, so that's equal to 0. And we're still left over with delta G naught, right? Okay, if we manipulate this around, we can isolate some stuff on one side. We want to get delta G by itself, or delta G naught. So what's delta G naught equal to?
Negative RT, natural log of K.
Yep. Okay, from a previous equation, you know another way to calculate delta G that you told me earlier. What else is delta G equal to? With some other thermodynamic properties.
Delta H minus T delta S.
Yep, exactly. And we care about delta G naught, so what we're going to do, we're going to make these knots here. Okay, now, if we have the equilibrium constant, we can easily calculate delta G, right? But what about H and S? Let's find a way. What could we do to find a relation between K and delta H and delta S?
Them equal to each other.
Yep, they're both equal to delta G. So what we could say is that we have negative RT ln K is equal to delta H naught minus T delta S naught, right? Okay, now we're going to do something a little tricky. We want to isolate this ln K by itself. So what would you do?
Divide RT.
Yep, divide by negative RT. So we get negative delta H naught RT minus, or actually what happens to this term if we divide by negative RT?
The T goes away and it becomes
goes-
positive.
Yep. Okay, but if you notice, this is a little bit different than the way that it's written in the lab. The way it's written in the lab is ln K is equal to negative delta H naught divided by R times 1 over T plus delta S over R, which seems like a pretty silly way to organize this. But why organize it this way?
Because when we graph it, we're graphing ln k and 1 over t, so then the slope will be delta h over r, and then
Right.
the intercept, we can find delta s over r.
Exactly. This is a linear relationship. Y is equal to mx plus b, right? What's our y again?
ln k.
Yep. What's our slope?
Delta h over r.
Mhm. Our x,
1 over t.
and finally our b is just what's left over, right? Our intercept. So Cindy, I think you said all we have to do, we just have to get the ln of k, we have to measure that equilibrium constant, we have to measure the temperature, or 1 over the temperature, and we have all the thermodynamic properties we need, which is pretty cool. So in this experimental setup, if you were conducting it, the way it would look is we would have our cuvette. We'd have a temperature probe in there. I don't know, we'll draw it, we'll color it, we'll make it pink or red. Okay, so we can measure the temperature that way. How are we going to measure the equilibrium constant? I don't see like an equilibrium gauge anywhere in the lab.
Through the absorbance.
Yep, so we'd be looking at absorbance. That's meant to be a light bulb, it's got a source. So what we're going to do is we're going to measure the temperature and absorbance. However, absorbance doesn't directly say anything about concentration, right? So how are we going to relate the absorbance to the concentration of the sample?
Here's law.
Yep. And again, what's Beer's law state? Absorbance is equal to what?
Like the curly E, B, C.
I like curly E, yeah. Curly E, B, C. What are these things again?
B is 1, right?
E is usually 1 centimeter. It's the path length. They build these things to be 1 centimeter long, so it makes our lives easy. C, what's C? That one's an easy one.
Concentration.
Yup. Concentration. And then that epsilon or curly E, as we so affectionately call it. What's that?
A molar constant or coefficient.
Yep, molar, whoa, except I can't spell it all. Molar extinction coefficient. And that depends on a couple things. So E depends on what things does E depend on? So think back to the other labs we conducted. In order to know epsilon, what did we have to keep track of? Or let me ask you, is this molar extinction coefficient going to be the same if I consider different molecules?
No.
Right, so it depends on molecular identity. Also, let's say I throw a spectrum up. So I'm going to put one up right now, which is poorly labeled. Do not do what I have done. Can everybody see this?
Yep.
So I got this spectrum here. We'll make it a little bit bigger. What other things do we need to keep track of? Or what should this x-axis be labeled with?
A wavelength.
A wavelength. So remember, epsilon also depends on the wavelength that you select. Okay? All right. I think that is all that you guys really need to conduct the lab. Are there any questions right now? Was that a good refresher for thermodynamics? Okay.